Hi, my name is Sandy. My friend Brooke and I decided to make a video about the fundamentals section of our textbook to help students review for any future tests and quizzes. This video will review the following topics: how to find moles and molar mass, finding the empirical formula and molecular formula, how to solve for molarity, learning how to balance chemical equations, finding what the limiting reactants and how much product can be formed in a reaction.
The first concept is learning what a mole is. 1 mole is the number of atoms in exactly 12 grams of carbon-12. 1 mole also has 6.0221 times 10 to the 23rd power of molecules, atoms, particles, and etc. This number is also known as the Avogadro's constant and is represented by the variable n subscript a.
The next concept is molar mass. The definition of molar mass is the mass per mole of particles. The units of molar mass is written as grams per mole. So, for example, the molar mass of carbon is known as 12 grams per mole. To find the number of moles, we use the equation mass of sample equals number of moles times the molar mass. So in this case, if we're looking for the number of moles, we take the mass of the sample and divide by the molar mass to get the number of moles. Once we have the number of moles, we can solve for the number of atoms by multiplying the number of moles by the Avogadro's constant.
Problem E9 of the fundamental section states, Epsom salts consist of magnesium sulfate heptahydrate. Write its formula. How many atoms of oxygen are in 5.15 grams of Epsom salts? How many formula units of the compound are present in 5.15 grams of Epsom salts? And how many moles of water molecules are present in 5.15 grams of Epsom salts? So first we're going to find the formula, which is MgSO sub 4 7H2O. And then we're going to go to A, where we found the molar mass of the compound, which is 246.48 grams per mole. So to find the atoms of O, we're going to start out with 5.15 grams, which will be divided by 246.48 grams per mole. And then this will be multiplied by 11 moles of O atoms, which you find from the compound, which 4O and 7O come out to 11. And then we multiply this by 6.26 times 10 to the 23rd atoms per mole, since we're finding the number of atoms. And this comes out to 1.38 times 10 to the 23rd atoms. For part B, we find the formula units by dividing 5.15 by 246.48 and multiplying this by the number of atoms, which is 6.626 times 10 to the 23rd, which comes out to 1.26 times 10 to the 22nd atoms. And for part C, when we find moles of H2O, we're going to take 7, which is from the formula again, and we're going to multiply that by 5.15 grams over 246.48 grams per mole, which comes out to 0.146 moles.
Next, we look at empirical formulas and molecular formulas. Empirical formulas show the relative number of atoms. So for instance, if we have CH2O, this shows the ratio between 1 carbon, 2 hydrogen, and 1 oxygen atom. Molecular formulas, however, show the actual number of atoms. So instead of CH2O, we have C6H12O6. To solve for an empirical and molecular formula, we start by finding the mass percentage composition of the compound, which is also known as the percentage of the mass of each element in a compound. To start, we assume that we have a 100-gram compound. Because of this, the mass percentage composition is the actual mass of each element. We use this mass to convert into moles. We divide the moles of each element by the smallest value among them. But the thing to keep in mind, however, is that we have to have whole numbers. So if one of the values turns out to be 1.33, we will have to multiply each of the moles by 3. This is also known as the empirical formula. To find a molecular formula, we have to calculate the molar mass of the empirical formula. Once we have that, we use the molar mass of the whole compound, which is usually given to us, and we divide that by the molar mass calculated by the empirical formula. After doing this, we have a factor, which we multiply the empirical formula by to get the molecular formula.
So for question F14 from the textbook, we're trying to find the empirical formula. So we have 4.69 grams of sulfur combined with fluorine to produce 15.81 grams of this gas. So we're going to find the percent mass of the sulfur, which we do by taking what they give us, so 4.69 grams, divided by the total mass of the gaseous form, so it's 15.81. And this comes out to about 0.297, which we multiply by 100 to get the percentage, which is 29.7%. We do this again with fluorine, and we get that 11.12 by subtracting 4.69 from 15.81. And we put this over 15.81, which comes out to about 0.703 times 100, which comes out to 70.3%. So from here, we assume that we were given 100 grams of sample, so we just change these percentages to grams. So the moles of sulfur would be 29.7 divided by 32.065, which is its molar mass from the table, and we get 0.925 moles of sulfur. And then for fluorine, we do the same thing with 70.3 over 18.998, and we get 3.7 moles. So to find the ratio, we divide by the smallest number, which is 0.925. So for sulfur, we get 1, and for fluorine, we get 4. So there is 1 sulfur for every 4 fluorine, so we get SF sub 4.
Next, we study molarity. Molarity is given by the equation molarity equals moles of solute divided by the volume of solution. The volume is given in units of liters, represented by the capital letter L. Molarity is in units of moles per liter, given by the abbreviation of a capital M. When we dilute a solution, increasing the volume of a solution, the moles of the solute does not change. Given this, we have an equation M initial times V initial equals M final, V final.
So for this question, we're trying to find the molarity, and then we're going to take this and use it to find the moles. So we have 1 liter to start with, so that'll be our V initial, and then we have 0.2 moles of this compound. So we'll use that as our molarity, and then MV initial equals MV final, so our final volume is going to be 4 liters because we're adding 4 or 3 to 1. We get 4. So once we do some multiplication and division, we get that our final molarity would be 0.05. And then we take this and we use it with the equation N over volume, which would be moles over the volume. So we get 0.05 equals N over 0.1 liters. So then we multiply 0.1 by 0.05, and we get 0.005 moles. So then we're trying to find the moles of nitrogen. So notice that there are 2 in the formula. So we multiply this answer by 2, and then we get 1 times 10 to the negative second moles of nitrogen, which we write it that way so that we have our significant figures right.
An important concept to remember when balancing chemical equations is that because of the law of conservation of mass, the total number of atoms on the left, the reactants, must equal the total number of atoms on the right, the products. To do this, we use stoichiometric coefficients, which are figures, numbers, that we add to the front of each compound to try to balance the equation on both sides. An important rule to remember, however, is that subscripts cannot be changed. So for instance, if we are given the compound of H2O, the 2 cannot be changed at all. We can only add coefficients to the front of the compound. Another important thing to note is that when a compound is said to experience combustion, it means that the compound is reacting with oxygen, which in many cases will produce carbon dioxide and water. An example of how to balance chemical equations is if we are given the equation of NH3 plus O2, which gives the product NO plus H2O. In order to balance this, we have to have the same amount of nitrogen, hydrogen, and oxygen on both sides of the equation. When you look at the first solution here given, 2NH3 plus 5/2O2, yielding the product of 2NO plus 3H2O. You have to remember that fractions are not allowed. We have to multiply out the fraction, giving a final answer of 4NH3 plus 5O2, giving this products of 4NO and 6H2O.
So the idea is that the limiting reactants limit the amount of product that can be formed. So the mole ratio takes the substance required divided by the substance given, which equals the moles of B divided by moles of A. So to find the limiting reactant, we have to balance our equation first, and then we choose one reactant and calculate the number of moles, and then we multiply this number of moles by the mole ratio between the two reactants to get the number of moles of the second reactant. So if the number of moles of the second one is less than the number provided, then it's the limiting reactant, and if it's greater, then the first one is the limiting reactant. So to find the amount of product that can be created, we use this limiting reactant, and we multiply it by the moles of limiting reactant to the mole ratio between the limiting reactant and the product to get the number of moles for the product. So to convert this number of moles to the product to mass, we multiply it by the molar mass, and that gives us the amount of product. For the following equation, determine the limiting region if the 21.4 grams of NH3 is reacted with 42.5 grams of O2. So we are given this equation, and so first we have to balance it. So in a previous question, I believe we balanced it. So we choose one reactant. So we're choosing NH3. So we're going to do 21.4 grams of NH3, which is given to us, divided by 17.03 grams per mole of NH3, which is molar mass. So then we get that we have 1.26 moles of NH3. So then we're going to use this mole ratio, and we're going to take it and we're going to multiply it by 5 moles of O2 over 4 moles of NH3. So this is going to give us the moles of O2, and then we're going to multiply this moles of O2 by its molar mass to find the grams of O2. So O2 is the limiting reagent because the amount given is 42.5 grams when 50.3 grams is needed to react with NH3.